Alrighty, so what we're going to do in this little video is we're just going to practice a little bit of chapter 18 since most of the chapter is finished, just with a few problems to kind of help tie together the concepts, prepare for the quiz, and just make sure that we're understanding it. And really, my goal for this is for you guys to kind of visualize what type of questions can be asked from this material. So, what is the best oxidizing agent and what is the best reducing agent from the following? Explain why. So I put reduction tables here. Know that sometimes half reaction reduction tables will be given like on the front cover or back cover of a quiz or exam. And if you have this question, you'll have to look for that. It might not be given exactly underneath the question like it is here. Now, before I even look at all of these substances that I have, I want to think of what does it mean to be a good or the best oxidizing agent, and what does it mean to be the best reducing agent? Well, to be the best oxidizing agent, it means that it's most easily reduced. So that means highest potential energy, highest cell potential. Well, best reducing agent means most easily oxidized. So that has the highest oxidation, which would be the highest potential when you flip the reaction. So remember that all of these half reactions are always given in the reduction form. So we're trying to figure out which is the best in the oxidizing. So we have to flip the reaction and find highest inverse. I keep spelling highest wrong. Highest inverse cell potential, because it's the opposite process. All right, so kind of now that we figured out what we're looking at, let's look at all the substances that we have. So we have sodium, and these are the two tables from the slides. Now, in your book, or even online, these tables are really, really large. So if they're not on these tables, then you would look it up. And sodium is not on these tables, so I would look it up, and I find that, well, sodium reduction reaction is the following. Bromine, can I see bromine on my table? I do, bromine's right here. So I have bromine plus 2 electrons gives me bromine ion. And you do not have to write, like I'm writing, every single one out. It's just, for me personally, I like to do that so I can help visualize what's going on. And then I have, because I just did my this, and now I have my cobalt and my cobalt 2+. Let's see, is cobalt on my little chart here? Oh, I did have sodium. Alrighty, cobalt. I know it's on here. Oh, there it is. Right there, cobalt. So then you have CO2 plus 2 electrons to 2 CO, no, just CO. And that is 1.82. Oh, because that's not the same one. Nope, that's not the right one. This is to minus. So we have to look at the one that I found, which is negative 0.28 volts. Then we have the iron and iron 2+. So here's the iron 3+. Where's my iron 2+? Boom. So iron 2+ plus 2 electrons makes iron, and that's negative 0.44. And then I have iron 3+ plus 3 electrons to iron. I already found that one, and that was 0.037 negative. volts. These are all volts, even if I'm not writing volts for every single one of them. And then boom, boom, boom. And then I have hydronium ion. Now, where's my hydronium ion? Da, 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 da. All right, I don't think the hydronium is on here, so you would look at another resource. It would be given to you, and the hydronium is 2H3O+. 2 electrons makes hydrogen and water, and that's actually 0. And then our last one is gold, which is 1.498 volts. Okay, so you're looking at your cell potentials. Now, let's first figure out which one is the most easily reduced. So which one has the highest cell potential? Gold, right? 1.498, without flipping it, because we're looking at reduction, so we're looking at that forward direction, is the highest cell potential. So gold 3+ is most easily reduced. Now, what about most easily oxidized? So imagine, you don't even have to actually do this, but imagine flipping the rest of these. So if you flip all of these that are remaining, except that, because that would just be 0, which one would be the best reducing agent, so most easily oxidized? Well, it's going to be the more negative one, because the most negative, if we flip it, will be the highest positive. So therefore, sodium, because if we flip it, we have Na to Na plus electron, and the inverse of this, 2.71. So then sodium is most easily oxidized. And it kind of makes sense because it's such a reactive metal. Awesome. Let's look at another question. So imagine you are performing the electrolysis of sodium fluoride. So let's write what sodium fluoride. Sodium fluoride is NaF, using copper electrodes. So that would mean if we have a copper electrode, we have copper and copper 2+. What half reaction would occur at the anode and what half reaction would occur at the cathode? Predict all half reactions that are possible. Okay. So electrolysis, right, means non-spontaneous reaction. And we think of the anode on the left, guiding electrons through a power source to the cathode on the left, the anode's one on the right. And it's non-spontaneous, so opposite things are happening of what we usually would see. So therefore, the sodium would be the reduction, and the fluorine would be the oxidation. So because sodium fluoride is an aqueous substance, this only happens in water. So let's first write down what's actually present. I have my sodium ion. I have my fluorine ion. I have my copper electrode. And I have water. So all of these can contribute to either oxidation or reduction or both. So then what you want to do is you just want to write out everything that you possibly could have and then kind of figure out which is the best, meaning which would exist at the cathode or the anode. So possible reductions. Now again, because this is an electrolytic cell electrolysis, it's non-spontaneous. So we know that the sodium is being reduced. So Na plus an electron goes to sodium, and the cell potential is negative 2.71 volts. Now, possible oxidations, I'm just going to kind of do both at once. Since I just figured out my sodium, I know my fluorine is going to be oxidized. So I have 2 fluorines. And again, you would just look up these half reactions on your table. You would find where your sodium was, which is I already did. Then you would find where your fluorine is, which is right up here. But what you want to remember is, so if I go back up here actually, this is the reduction, right? So you have to actually flip this. So you start with your ion and you go towards your electrons because it's oxidation. So you flip the reaction and you would get this. And since you flipped your reaction, your cell potential would be negative 2.87 because you flipped it. Okay, so now we just dealt with the sodium and the fluorine. Now what would the water do? We already talked about how the water, can do both, because water can exist as an acid or a base. It can exist as an electron pair donor or acceptor, so it can also exist as oxidizing or reducing. So we actually have to look at both possibilities before we can decide which one's actually happening. So you would write one possible reduction for water and one possible oxidation. And then oxidation would be 2H2O, O2 plus 4H plus 4 electrons. And these numbers are coming from the table, just looking at the possible oxidation or reduction of when water would be acting as an acid or a base, right? So this would be a basic substance, this would be acidic. Knowing that in order to be acidic, it has to be oxidized. In order to be basic, it has to be reduced, right? Because in order for hydroxide to form, the electrons have to be gained. And in order for hydrogen ion to form, the electrons have to be lost so that the oxygen can break off. Alrighty, so now we have one more left. We have copper. So is copper also going to do both? No. We just have copper, and copper is a metal. Now, because it's acting as an electrode, it's going to act in that way. It's going to act as metal. So metals aren't usually reduced, so then copper is a possible oxidation. So we find what copper would be on the table, and then we would flip that because it's oxidation. And that's copper 1. Do we have copper 2 on this table? Also copper 1. Copper 2, perfect. So then Cu2 plus 2 electrons, flipping that would then be copper, 2 electrons, and then Cu2 plus, and the cell potential is, flipping that, 0.337. All right, so these are all your possibilities. Again, knowing that when you have an ionic compound, you have the two ions. Since this is electrolysis, it's non-spontaneous, so the metal is being reduced and the non-metal is being oxidized. And whatever electrode you have, it will act as its normal state. So if it's a metal, metals are usually oxidized, so that's also part of your oxidation. And since the electrolysis of an ionic compounds split up into ions in water, not just on their own. So then you have the possibility of water. Knowing that water has basic and acidic functions, you write the half reactions where one produces a base and one produces an acid. Knowing that a base would be reduction and an acid would be oxidation. All right, so we have all of our information. Now, I totally forgot what the question was. It says what half reaction would occur at the anode and what would occur at the cathode, and predict all half reactions. So we already did that. So now we just want to figure out which one would be cathode and which would be anode. So essentially you're looking at which is the most reductive possibility and oxidation possibility. So from the question earlier, we know the best oxidizing agent, the most easily reduced, has the highest reduction potential. So from all possible reductions, which one would be most easily reduced? Water. So water would exist at the cathode or the anode? Cathode, because it is reduction. Now, out of our possible oxidations, which one is the most easily oxidized? So we already flipped them, right? So which one has the highest number? This one, easiest. oxidized, so it is at the anode, the copper. Awesome. So this is how we kind of look at different half-cell reactions. That's what we did up here. But then down here, we actually put the term electrolysis to it. So we had to think a little bit more about what those cells would look like, those half reactions, what needs to be flipped, what has more than one possibility, etc. All right, let's get to a little bit of math. Calculate the time required to plate out 10 grams of chromium on an object from a solution of chromium 3 plus with a current of 2.6 amps. Calculate the maximum amount of work in kilojoules needed to produce 10 grams of chromium from a solution of chromium 3 plus with an applied voltage of 1.75. Alrighty, so this is two questions. Here's my first and here's my second. So if I look at just my first question, I have the mass of chromium. I have 10.0 grams of chromium. And I'm putting this on chromium ion. And I have a current of 2.60 amps. Well, I know that 1 amp is a coulomb over second. So 2.60 amps is 2.60 coulombs per second. So this is everything that I'm given here, right? Now, what do I want? Calculate the time required to plate out yada, yada, yada. So I want time. So that means I'm looking for seconds, hours, minutes, doesn't really matter. It doesn't say specifically, but it does say time. And if I look back at everything that I'm given, I know that I can get time from my 2.60 amps because that gives me seconds. So then I kind of make myself a plan. So if I want seconds in the end, right, that means I would have to have my seconds on the top and my 2.6, I just wrote that wrong, oops. My seconds on the top and my 2.60 coulombs on the bottom. Well, that means I need to get rid of coulombs. Well, I know that my one constant that has coulombs in it is Faraday's constant, which is 96485 coulombs per mole electron. Well, if I multiplied this by my Faraday's constant, I could get rid of my coulombs and have time. But now I have this mole of electrons and I still haven't used my 10 grams. So then I kind of start to think, all right, well, moles of electrons, that means I need to think of what happens from chromium to chromium 3 plus. Well, chromium ion gains 3 electrons to become chromium solid. So for 1 mole of chromium, I have 3 moles of electrons. And therefore, to get rid of mole electrons, I use, my conversion factor. So 1 mole, 3 moles of electrons over 1 mole chromium. Well, then I have to get rid of my chromium, which I can do by starting out with my 10 grams. So if I take my 10 grams of chromium and multiply with the molar mass, divide that, I can then get rid of my grams chromium, moles electrons, coulombs, and I get seconds in the end, which would equal to 2.14 times 10 to the 14th seconds. Now, usually we don't want seconds. We would want minutes or hours just because this is a really large number. So if I converted this to hours, I could do 1 hour over 3600 seconds. Or you could split it up. It really doesn't matter. The reason I'm converting it and it doesn't tell you to convert to what specific time is because the seconds is a really, really high number. So we're just trying to simplify that a little bit. This would give me 5.95 hours. Now, the question would come up, do we have to convert? And I do want you to actually critically think about that. So even if it doesn't say specifically to convert to a unit, I want you to think, okay, well, if your seconds number is really, really small or really, really large, what unit could you convert to time to make it a more simplified number? So we kind of worked backwards, but you could also work forwards, realizing I have 10 grams and I have these amps. Since I want time, I know I have to use the coulombs per second. I know Faraday's constant. Well, since there's moles in there, I have to convert my mass to my moles, which would give me molar mass. And the only way you can get from chromium to mole electron is writing the half cell reaction, which we did here, and then kind of working your way forwards. Awesome. Let's look at the next one. So I'm going to kind of draw a line here. Next question. Calculate the maximum amount of work in kilojoules needed to produce 10 grams of chromium. So I'm still given my 10 grams chromium from a solution of chromium ion with an applied voltage of 1.75. So my applied voltage here is 1.75 V. And I want work. Well, what's my equation that I know for work? I know work is equal to NF E cell or E external. Okay, well, what's N? N is for moles, right? F is Faraday's constant, and E is cell potential. Well, I already have my cell potential. I know Faraday's constant because it's a constant, and moles is from my half reaction up here, which would be 3. So then you would have work is equal to 3 times 96,485 coulombs per mole of electron, since this is mole electron, that's canceled out, times the cell potential, 1.75. Now, volts, but volt is also joules per coulomb. So instead of writing volts, I'm going to write joules per coulomb, because then you can see moles, electrons go away, coulombs go away. You're left with 5.0645 times 10 to the 5th joules per, there's no moles of electrons here actually. This is just 3 since we're just using the number, joules per mole. So then what I want you to think of is, okay, I want just kilojoules, right? Well, I know to get kilojoules, I can divide that by 1,000, but I have to get rid of the moles. So that's where that 10 grams comes in. If you take 10.0 grams of chromium and divide by the molar mass, you get 0.1923 moles. That multiplied by 5.0645 times 10 to the 5th joules per mole will get rid of your moles, and you would be left with 9.74 times 10 to the 4th joules, and you want kilojoules, so then you divide by 1,000 to get 97.4 kilojoules. Now, in your work equation, you're just using the number N, no unit, knowing that Faraday's constant is always per mole, so when you're calculating work, you're always left with joules per mole. Now, if it didn't say specifically kilojoules, then you could have left it like that, but since it said in kilojoules, you not only had to convert to the unit kilo, so dividing by 1,000, but also get rid of that mole. And this is where that mass came in, because converting to moles from there and multiplying it by that work amount, that energy amount, you were able to figure out just the energy from the amount of moles and then convert to kilojoules. All right, let's look at the last 2 little practice questions. Consider the reaction shown below at 25 degrees Celsius. Determine the cell potential and equilibrium. This is supposed to be constant. For the reaction when the concentration of the ions are both 1 molar. The standard Gibbs free energy for the reaction is negative 14 kilojoules. So I'm just going to write it next to it. Awesome. So I want cell potential and I want my equilibrium constant. Well, how does everything relate? I know that my cell potential is equal to standard cell potential minus 0.0592 over N log Q. Q I always have because Q is going to be products over reactants. Since two of them are solid, it's just A over B2 plus. What else do I know? Now I'm just going to write out my little equations here. I know my Gibbs free energy, which I have given, is negative NFE cell. I also know that my Gibbs energy is equal to the standard Gibbs free energy plus RT ln Q. All right, what else do I know? There's one more where the equilibrium constant comes into play. And then just given the concentrations and the Gibbs free energy standard of the reaction, how can you solve for what you want? So I'm going to give you a moment here to think about it and look up that last equation. And actually I want to ask you another question. Do I even need another equation, or do I have everything that I need here? Now my one more equation, I'm going to write two more that we know. Delta G standard is equal to negative RT ln K. And we also know that the cell potential is equal to 0.0592 volts over N log K. Alrighty, so I know a lot of stuff. So where do I start? Well, you're given this piece of information, so you kind of have to start with this, right? And the concentrations. So I can use my Gibbs free energy and my R constant to solve for my equilibrium constant. And then how can I use that to solve for my cell potential? Well, since I want the cell potential, not the standard cell potential, I will have to use my Gibbs free energy here to solve for my cell potential standard and then plug it in to get my overall cell potential. So then if I have delta G naught is equal to negative RT ln of K, right? So then that would be R is what? 8.314 joules per mole Kelvin. So delta G is in kilojoules. Would I need to convert? Yes. Now again, sometimes you'll see that they actually convert R. I don't ever do that because I just don't like to. I think it's always easiest to convert everything else but the constant. But again, there's no rule that you can't convert the constant to the appropriate units. It's whatever way you feel most comfortable and confident. So I know kilojoules to joules times 1,000, nice and easy. So negative 14,000 joules times negative 8.3145 joules per mole Kelvin. T, temperature 25 degrees Celsius, so 298.15 Kelvin. Ln of K. Alrighty, so I still have to do this problem. So one step at a time, try to solve this. 8.3145 times. And then that negative 14,000 divided by negative 2478.968. So I get, multiply these, divide over, negative goes away, 5.6475 is equal to ln of K. Now how would I get rid of ln? You take the E, right? And then K is equal to 283.58. We want 3 sig figs, so 284. All right, so now we want to solve for the other cell potential. So then we want, okay, delta G is equal to and if I'm solving for E cell, my delta G standard would be negative NF. So I have Since Faraday's has coulombs in it, can be converted to a joule, that would be 14,000 joules divided by negative N. What would be N? I have 2 charge, so 2 electrons. Faraday's constant 96485 coulombs per mole. And that would be what? 14,000 divided by 2 times 96485. 0.0726 volts. Because it'd be joules per coulomb, which would just be a volt. Awesome. So then I now can use that here to solve for my last little bit. N would be 2 times log of Q, and log of Q would be the A2 plus, which is 1 molar, over B2 plus, which is 1 molar. So then log of 1 divided by 1 is 0 times 0.0592 over 2 is 0. So then your cell potential is 0.0726 volts. So then you solve for everything. So you don't have to go exactly the way that I went. I just like to write out all my equations to kind of see which ones I can use with the given information that I can have. And we weren't given a lot of information in this problem, so it's kind of like working backwards where you can implement 2 different equations into one. Okay, last one. The cell potential of this electrochemical cell depends on the pH of the solution in the anode half cell. What is the pH of the solution if the cell potential is 355 millivolts? So here's our cell. So it's written in that notation. So remember that the singular line are phase change, and the double line is that salt bridge. So on the left of this is the anode, and the right is the cathode. So I have my hydrogen forming the H plus, where we don't know the concentration, so that's where the pH is coming from. pH is equal to negative log of H plus or H3O plus. And the platinum is there to use as an electrode since it's not in a solid form. And then we have the information for copper. So what I'm going to do is I want to figure out my pH. Well, if I want to figure out my pH, I need my hydrogen ion concentration. So using cell information, I know that my E cell is equal to the standard cell potential minus 0.0592 over N log Q, where Q is the concentration of the products over the concentration of reactants. Okay. So I'm given the cell potential. I have E cell. 355 millivolts is my E cell, my cell potential. I know I can get my standard cell potential from standard half reactions. So what I'm going to first do is look at my half reactions and find my overall equation to also get my Q then and know what my products are and my reactants. So cathode is the reduction, so I'm going to find my reduction equation for copper, and that's going to be, I'm going to give you a moment here to look it up on your own. So find the reduction reaction for copper and then write the half cell reaction for hydrogen, knowing that hydrogen is going to be flipped. So pause the video and try it on your own. Okay, hopefully you paused it. So then cathode is the copper being reduced. And then the anode is the hydrogen gas being oxidized. So then my overall reaction will be my overall cell potential, standard cell potential would be 0.34 volts. And then I can see my Q will be my hydrogen ion concentration squared over my copper. right? Well, I don't know my hydrogen, but what I do know is that my copper is 1.0 molar. So then this would just sum out to be that Q is equal to H plus squared. And then this is where I can get my pH from. Awesome. So let's kind of highlight what I need. So I have this piece of information, my Q, I have my cell potential, and I have my overall cell potential. So if I plug everything in, 335 millivolts would be 0.355 volts, right? Because there's 1,000 millis in an overall constant. So then we have 0.355 volts is equal to 0.34 volts minus 0.0592 divided by N, which is 2 electrons, times log of Q, which is log of H plus squared. So then you just calculate. So you subtract over your 0.34 on both sides. You get 0.015 volts is equal to negative 0.0592 over 2 log H plus. And now what I would do is I would leave the negative because pH is equal to negative log of H plus. So you should just multiply this, both sides, by 2 over 0.0592. So that cancels. So let's do that part. So 0.015 times 2 divided by 0.0592. So then 0.5067 is equal to negative log H plus squared. And then what we want to do is simplify that and solve for the pH. And then the pH comes out to be 0.25. And you're done. So it's actually implementing some of the stuff we've already learned, pH, with new stuff. So a lot of the times you'd think, well, I don't have a titration. Where do I get pH from? I'm only given volts, but it's kind of working a way backwards, knowing that since you're given the overall cell potential, you can always find this using half reactions, which you'll always have handy to you because you always have those tables. So the rest of it is, okay, well, I'm given my cell, so I can find Q because I can write an equation. So then it's just thinking of exactly what you're looking for. You know, are you looking for the cell potential? Are you looking for the concentration of one of these? Were you looking for another component, etc.? So it's just really understanding what all